Right. So, very good morning to you all. I welcome you all for today's EMF class. In my last class, I have discussed about Smith chart related problems. Now, one important problem I have considered, I have taken, and I have solved using Smith chart. Right. So, in this problem, I have determined almost all parameters related to transmission lines. That is reflection coefficient, voltage standing wave ratio, input impedance, the location of Vmax and Vminimum of a transmission line, right? So all those things I have discussed in my last class, right? So this is what I have discussed in my last class. I have written the procedure very clearly, right? So if you have any doubt, go through my last video so that it will be more clear to you, right? So let us move on to another topic for today. UHF lines as circuit elements. UHF lines as circuit elements. Right? So UHF lines. So what is meant by UHF lines? UHF transmission lines. Right? So UHF in the sense ultra high frequency. Right? UHF means ultra high frequency, which is in the frequency range of 300 megahertz to 3000 megahertz, right? The frequencies between 300 megahertz to 3000 megahertz is called as ultra high frequency, right? So that means what? The frequency is very high, right? At very high frequency. So frequency high in the sense angular frequency is also high, right? Omega is high, right? So therefore XL means J omega L, and XC is 1 by J omega C, right? So as omega is high, XL is very high, and as omega is high, XC is less, right? XC is less, and as we know that the transmission line electrical equivalent is this. So in series we have resistance and inductance, and in parallel we have conductance and capacitance, right? So this is the electrical equivalent R, L, G, and C, right? Resistance, inductance, G is the conductance, and capacitance. Conductance and capacitance are in parallel, right? So therefore, as X is less, G can be neglected at very high frequency. So here conductance can be neglected because it is the parallel combination, and R can be neglected here, right? Because it is series element, right? So therefore the equivalent circuit, the equivalent electrical circuit at radio frequency or very high frequency is this, right? Is this L and C. So this is the electrical equivalent circuit at UHF frequency, right? So this is one unit length of transmission line, not the entire length of transmission line. So this is one unit length of transmission line, right? So therefore, at very high frequency, that is ultra high frequency, if you consider the characteristic impedance that we know, R plus J omega L divided by G plus J omega C, right? So at ultra high frequency, omega is much greater than R, right? And j omega is much greater than G, right? In other words, we can consider it as a low loss, right? Low loss, and that means j omega is very much for lossless. Lossless we have discussed. For lossless, R is equal to G is equal to 0, right? For a lossless transmission line, R is equal to G is equal to 0. But whereas for low loss, right? For low loss, it is j omega is much greater than R, and also much greater than G, right? So therefore, we can neglect R and G here. We'll get L by C, right? Characteristic impedance as L by C, right? Same, almost same for lossless transmission line. Characteristic impedance is also same, right? But whereas gamma, right? Gamma for lossless transmission line, alpha is 0, right? For lossless transmission line, alpha is 0 and beta not equal to 0. But whereas for low loss transmission line, alpha not equal to 0 and beta not equal to 0, right? So gamma is the propagation constant that we know, R plus j omega L and G plus j omega C, right? So applying this condition, right? So applying this condition, what is the condition? J omega greater than R and j omega greater than G. Applying that condition here, right? For this, and you will get expressions for alpha and j beta, right? Alpha and j beta, right? So that is about low loss transmission line, right? So here UHF lines as circuit elements, right? UHF lines as circuit elements in the sense here earlier we have discussed short circuited transmission lines, right? And open circuited transmission line, right? Short circuited transmission line, open circuited transmission line, and we have determined the input impedance, characteristic impedance, reflection coefficient, voltage standing wave ratio, and input impedance, right? So all those things we have determined for both short circuited transmission line and open circuited transmission line, right? So for example, input impedance ZL is equal to Z0 ZL plus J Z0 tan beta L divided by Z0 plus J ZL tan beta L, right? And here let us consider various lengths of transmission lines, right? Various lengths of transmission line, right? So that is, for example, L is less than lambda by 4, and L is in between lambda by 4 and lambda by 2, and L is equal to lambda by 4, right? Let us consider different lengths, right? Different lengths of transmission line, right? L is equal to lambda by 4, and if L is in between lambda by 4 and lambda by 2, and L is equal to lambda by 4, then let us see what is the input impedance, right? What is the input impedance at for ultra high frequencies, right? For ultra high frequencies, and um, um, you just remember the short circuited and open circuited transmission lines which I have discussed earlier, right? So let me took you to there. Yes, so this is the topic which I have discussed earlier, right? Open circuited and the short circuited transmission line, right? So short circuited transmission line in the sense when ZL is 0, right? When ZL is 0, for that we have determined the input impedance, right? Expression for input impedance. So this is the expression for input impedance of a short circuited transmission line. And importantly, we have drawn the variation of beta L, right? The variation of beta L with respect to the input impedance of the short circuited transmission line, right? So this is the variation, right? So here from zero to pi by 2, right? Let me, so from 0 to pi by 2 here, which you can see here, from 0 to pi by 2, the input impedance is inductive, right? The input impedance is inductive. And in between pi by 2 to pi, the input impedance is capacitive, right? Between 0 to pi by 2, the input impedance is inductive. And in between pi by 2 to pi, the input impedance is capacitive. And this is for short circuited transmission line, right? So pi by 2 in the sense what? Beta L, right? So this is beta L. Beta L is equal to 2 pi by lambda into L, right? 2 pi by lambda into L, right? So for example, if L is less than lambda by 4, right? If L is less than lambda by 4, then beta L is in between 0 and pi by 2, right? Beta L is in between 0 and pi by 2, right? So therefore, when length of the transmission line is less than lambda by 4, the input impedance is inductive, right? The input impedance is inductive for a short circuited transmission line. So therefore, it can be replaced as an inductance, right? It can be replaced as an inductance. So similarly, if L is greater than lambda by 4, right? If L is greater than lambda by 4 and less than lambda by 2, right? If L is greater than lambda by 4 and less than lambda by 2, then we can say that beta L is in between pi by 2 and pi, right? When beta L is in between pi by 2 and pi, we can say that the input impedance is capacitive from this graph, right? The input impedance is capacitive from this graph. So therefore, the equivalent circuit of the transmission line is a capacitor, right? For a short circuited transmission line. Similarly, for open circuited transmission line also, right? For open circuited transmission line, in between 0 and pi by 2, right? In between 0 and pi by 2, the input impedance is capacitive, and in between pi by 2 and pi, the input impedance is inductive, right? The input impedance is inductive, right? So you just keep these points in mind, right? So coming to here, short circuited transmission line. So this is short circuited transmission line, right? Let us say this is A, right? When length of the line is less than lambda by 2, right? When the length of the line is less than lambda by 2, its equivalent circuit is inductance, right? Its electrical equivalent is inductance, and input impedance is JZ naught tan beta L, right? Input impedance is JZ naught tan beta L, right? So we have seen, right? So since if L is lambda by 4, just now we have seen beta L, right? So beta L is in between beta L is in between 0 and pi by 2, right? If L is less than lambda by 2, beta L is in between 0 and pi by 2, right? So in between 0 and pi by 2, the input impedance is what? Just wait. So the input impedance is inductive, right? So if L is in between lambda by 4 and lambda by 2, beta L is in between pi by 2 and pi, and the input impedance is capacitive, right? You just remember this. If L is equal to, if L less than lambda by 4, beta L is in between 0 and pi by 2, and the input impedance is inductive, right? So previously from the graphs I have explained, if lambda by, if length of the transmission line is in between lambda by 4 and lambda by 2, then beta L is in between 90 and 180 degrees, and the input impedance is capacitive, right? So from this knowledge, here for a short circuited transmission line whose length is less than lambda by 4, the equivalent circuit is inductance, and for open circuited, right? So for open circuited transmission line, right, whose length is less than lambda by 4, the equivalent circuit is capacitive, right? The equivalent circuit is capacitive. So this is short circuited. So this is for short circuited, this one, right? So whatever I have discussed here is for short circuited transmission line. For open circuited transmission line, it is opposite, right? And input impedance is minus j z naught cot beta L, right? And similarly, see, for a short circuited transmission, again, let us consider a short circuited transmission line, but here let us consider the length of the transmission line is in between lambda by 4 and lambda by 2, then the input impedance is capacitive, right? The input impedance is capacitive, right? So therefore input impedance is minus j z naught cot beta L, right? And another case, let us consider another case here, open circuited transmission line, right? Open circuited transmission line whose length is in between lambda by 4 and lambda by 2, the equivalent circuit is inductive, right? The equivalent circuit is inductive. So therefore input impedance is j z naught tan beta L, right? J z naught tan beta L. And let us consider another case, right? For short circuited transmission line, if L is equal to lambda by 4, right? If L is equal to lambda by 4, L is equal to lambda by 4 in the sense what? Beta L is equal to 2 pi by lambda into lambda by 4, and this is equal to pi by 2, right? So when beta L is 90 degrees, right? When beta L is exactly 90 degrees, right? So if beta L is exactly 90 degrees, what is the input impedance of short circuited transmission line and open circuited transmission line? Let us go back again for open circuited, for those graphs, open circuited and short circuited transmission lines. This one, no, not this one, this one, right? So this is the graph for short circuited transmission line, right? So when L is equal to, when L is equal to lambda by 4, beta L is equal to pi by 2, that means 90 degrees, right? So exactly at 90 degrees, what you can see here, exactly at 90 degrees, what you can see here, it is here it is inductive, and here it is capacitive, right? Exactly at 90 degrees, it exhibits it exhibits both inductive and capacitive, right? At 90 degrees, it exhibits both inductive, less than 90 degrees inductive, greater than 90 degrees capacitive, but exactly at 90 degrees, it exhibits both inductive and capacitive, right? Inductive and capacitive, right? So therefore, if for a short circuit transmission line, L is equal to lambda by 2, then the electrical equivalent circuit is the parallel combination of inductance and capacitance, right? Parallel combination of inductance and capacitance. And similarly, for open circuited transmission line, if the transmission line is open circuited and length of the transmission line is equal to lambda by 4, right, is equal to lambda by 4, then the equivalent circuit is the series combination of inductance and capacitance, right? Series combination of inductance and capacitance, right? So this is about the UHF lines as circuit elements, right? UHF lines as at ultra high frequencies, right? At ultra high frequency means we are neglecting resistance, and G, right? Resistance and G, right? We are not considering resistance and conductance elements, right? So only we are considering inductance and capacitance. So that is the reason why in the equivalent circuits, right? In the equivalent circuits, we have inductance and capacitance, right? So this is about UHF lines as circuit elements, right? So when at UHF, right? So all these transmission lines are for UHF frequencies, right? So when L is less than lambda by 4, what is the circuit element? Inductance. When L is less than lambda by 4, what is the circuit element? Capacitor. And if L is in between lambda by 4 and lambda by 2, what is the circuit element? Capacitance. And similarly for open circuited transmission line, it is inductance. And if L is equal to lambda by 4, for short circuited transmission line, it is the parallel combination of inductance and capacitance. And for open circuited transmission line, it is the series combination of inductance and capacitance, right? And the input impedance is Zn is equal to Z0 square by Zl. And for here also, Zn is equal to Z0 square by Zl. Right? So this is the input. Right? So this is the last topic, right, in unit 2, right? Transmission line 2. Right? So with this we have completed second unit, right? So let me go back to the syllabus so that you can see clearly here, right? So in unit 2 we have discussed input impedance relations, short circuited and open circuited lines, reflection coefficient, VSWR, low loss radio frequency. Just now I have discussed low loss, right? And UHF transmission lines and UHF transmission lines as circuit elements that I have discussed now. Impedance transformations, lambda by 8, lambda by 4, and lambda by 2 lines. Smith chart we have discussed, and impedance matching techniques, that is quarter wave transformer and stub matching, right? So these are the topics which we have covered in unit 2, right? So with this we have completed 2 units so far, right? Unit 1 transmission lines 1 and unit 2 transmission lines 2, right? And before I enter into unit 3, that is electrostatics, let me introduce, right? Let me give introduction to that. Electrostatics. Introduction, right? So unit 3, let me give an overview of this one, right? Right. So as I said earlier, EMF, electromagnetic field theory, and transmission lines, right? Electromagnetic field theory and transmission line is a combination of EMF and transmission lines. So transmission lines, part 1 and part 2 we have completed. These two we have completed. And coming to EMF, EMF is divided into 3 sections, right? So one is electrostatics, and another one magnetostatics, and another one EM waves, right? In other words, time varying fields, right? Time varying fields, electromagnetic fields or time varying fields, right? So actually, um, EM wave, EM wave in the sense what? Electromagnetic wave, right? Electromagnetic wave, right? So what is the purpose of electromagnetic wave? The purpose of electromagnetic wave is to carry, right? To carry information in the form of energy from one place to another place, right? The purpose of EM wave is it is used to carry, right? It is used to carry information in the form of energy from one place to another place, right? So that means EM waves radiates, right? EM waves radiates. That means they travel, right? EM wave radiates or travel. Travel where? In space, right? Travel where? In space, right? Or free space, right? Or free space. Not only they travel in free space, they also travel in dielectric media, right? And they also travel in conducting media or different medias that we will discuss later, right? How the characteristics of EM wave changes in different media. So those things we will discuss later, right? So EM wave radiates. How they will be radiated into the space? By using antenna, right? Using antenna, we can radiate EM waves into this space, right? We can radiate EM wave into this space. So therefore, our main purpose is to understand EM wave, right? Our main purpose is to understand EM wave, right? How EM wave can be generated, and what are the characteristics of EM waves, and what are the mathematical equations of EM waves, and how they will be traveled in different media, all those things we are going to study, right? So if we go directly into EM waves, if we start studying EM waves directly, we cannot understand, right? We cannot understand. So that is the reason why we will study electric field separately and magnetic field separately, right? So first of all, we will try to understand, right? So initially we will try to understand what is electric field, and then magnetic field, and then once we are well aware about electric and magnetic field, then we can understand EM waves very clearly, right? So as we are studying electric field and magnetic fields individually, right? So therefore they are called as static fields, right? They are called as static fields, right? Both electric and electric field and magnetic field, right? They are individually, they are static in nature. Static in the sense what? Static in the sense stationary, right? Stationary in the sense will not travel, right? Will not travel. They cannot travel on their own. That means electric field cannot travel in the space. Magnetic field alone cannot travel in space, right? Whenever electric and magnetic fields are combined, then only they will travel, right? Whenever electric and magnetic fields are combined together, then they will travel, right? So therefore electric field alone is static, magnetic field alone is static, right? So therefore electrostatics and magnetostatics, right? So this is unit 3, and this is unit 4, and this one is unit 5 as per the syllabus is concerned, right? So electrostatic fields here, electrostatics, right? So in this unit we will study about we can say that electrostatic fields, the entire concept revolves around two concepts, right? The entire electrostatic fields revolves around two basic concepts, right? I can say that those two are the pillars for electrostatic fields, right? So number one is Coulomb's law, right? Coulomb's law, and second one is Gauss law, right? Coulomb's law and Gauss law, right? So Coulomb's law and Gauss law are used to determine, right? They are used to determine electric field, right? Electric field at a point in space, right? Coulomb's law is used to determine electric field at a point in space, and Gauss law is also used to determine electric field at a point in space. How we can determine electric field using Coulomb's law and Gauss law, those things we will discuss later, right? So similarly, magnetostatic fields, right? Magnetostatic fields, again magnetostatic fields also revolves around two basic concepts, in other words two basic principles, right? So number one is Biot-Savart's law, and second one is Ampere circuit law, right? Biot-Savart's law and Ampere's circuit law. Biot-Savart's law and Ampere's circuital law are used to determine magnetic field, at a point in space, right? At a point in space, and those things we will see in the coming classes. And similarly, electromagnetic fields, right? Electromagnetic fields, and here also it revolves. Electromagnetic fields, it revolves around um, two basic concepts, right? Around two principles, basic principles. Number one is Faraday's law, and second one, modified Ampere's circuital law, right? Electromagnetic fields, again it revolves around two basic principles. One is Faraday's law, and second one is modified Ampere's circuital law, right? Modified Ampere's circuital law, right? And all this one, from all this here in electrostatic fields, we will define two Maxwell's equations, right? We will define two Maxwell's equations, and here in magnetostatic fields we will define two Maxwell's equations, right? So from electrostatic fields, two Maxwell's equations, and from magnetostatic fields, two Maxwell's equations, right? So Maxwell's equations are very, very important. Without Maxwell's equations, there is no EMF, right? So Maxwell's equations are the heart of EMF, right? So only through Maxwell's equations we can understand how EM waves can be generated, right? How EM waves can be generated, right? And electrostatic fields, two Maxwell's equations, and magnetostatic fields, two Maxwell's equations, and together we have four Maxwell's equations, right? We have four Maxwell's equations for static fields, right? For static fields, right? And again, in electromagnetic fields, we will define another four Maxwell's equations, right? Four Maxwell's equations, right? And these Maxwell's equations are for time varying fields, right? These four Maxwell's equations are for time varying fields, right? So therefore, overall we have two sets of Maxwell's equations, right? So one set of Maxwell's equation is for static field, and another set of Maxwell's equations is for time varying fields, right? So we have different Maxwell's equations for static fields, and we have different Maxwell's equations for time varying fields, right? So those things we are going to study in EM waves, right? That is unit 3, unit 4, and unit 5. All those things we are going to study, right? So very easy. Transmission lines, comparatively it is easy, right? So far we have studied transmission line 1 and transmission line 2. I think you have not faced any difficulty while understanding the concept, right? So because we are using the circuit elements, right? We are using the circuit elements, right? Circuit elements in the sense resistance, capacitance, inductor, capacitor, right? All those we are using. So, and Kirchhoff's voltage law and Kirchhoff's current law, we are using those, and we have studied. But whereas EMF, we use field theory, right? Field components, circuit components, field components in the sense electric field, magnetic field, right? Electric field, magnetic field. There in transmission line, voltages and currents. In transmission line, voltages and currents. And whereas in EMF, it is electric field and magnetic field, right? And their input impedance or characteristic impedance, and here intrinsic impedance. Right? Almost the same things here also we will study, but with a different terminology. Right? So that is about the brief introduction of EMF. Right? So in the next class we will start unit 3, that is electrostatic fields. Right?